LADCAP, or Launchable Automatic Device for Capturing Airborne Particles, is a small device used to harvest particles from the atmosphere. This can be launched on a rocket, balloon, drone, or other small aeronautical vehicle. What we collectively call dust is actually a combination of particles of biologic and non-biological origin. My own interest focuses mainly on bacteria and bacterial endospores, but this device could be used for almost any particulate harvesting. As can be seen in this satellite imagery, dust in one part of the world can be scooped up by the wind and transported en masse across to other parts of the world. On the left, dust from the Sahara Desert can actually cross the entirety of the Atlantic Ocean and end up in Europe or the Americas. On the right, volcanic dust from a volcano in the Aleutian Islands can be transported across the Pacific Ocean. Likewise, biological dust in the form of bacteria, spores, and pollen can be transported long distances through the atmosphere. Global dust transport is not limited to Earth. On Mars, periodic dust storms cover the entire planet, and in fact this is probably what gave 19th century astronomers the illusion that Mars had vegetation that changed with the seasons. Nevertheless, fine dust particles do cover Mars and can be transported planet-wide. Airborne dust also has astrobiological implications. While the current surface of Mars is probably inhospitable to life as we know it, more protected areas might still preserve life either in an extant form or in a fossilized form. In either case, in 1991, Thomas and Schimmel proposed that wind could take the place of water as a means of transporting microbes, spores, and nutrients from one point to another on Mars. Again, we don't think this is probably happening today, but it may have happened in the past, and is certainly worth looking at. The LADCAP device is relatively simple. As shown here, it consists of a membrane filter holder that is autoclavable, inside of which is a standard 25mm membrane filter. This is attached to a vacuum pump, which is powered by a 9-volt lithium-ion battery. The lithium-ion battery is used because it's about half the mass of a 9-volt alkaline battery. As shown, this is mainly for testing purposes. For flight sampling, we would have to have switches that would activate the pump only at the altitude that we want and then deactivate it again when we're done. In more complicated varieties, we could also add an altimeter or a timer or other devices to finely tune when sampling occurs and how long a duration is used. In its form here, it has a total mass of about 120 grams, which makes it liftable by most rockets, balloons, and even some drones. The cost is relatively low as well. The prototype shown here cost less than $30. After LADCAP has been returned to ground, the membrane filter can be removed aseptically and either transferred directly to growth media and cultured, or examined microscopically, either using optical or electron microscopy. As I mentioned earlier, because of its relatively small size, LADCAP can be lifted with a variety of consumer-level launch platforms. This includes weather balloons, mid and high-power rockets, and some types of drones. Coming up next, we'll look at some of the pros and cons of each of these. Balloonsats, rockets, and drones have overlapping capabilities. Weather balloons historically have been used for atmospheric research, including the harvesting of pollen, dust, and other particulates from the atmosphere. However, they're typically uncontrolled and can easily drift horizontally much farther than they travel vertically. Rockets have a much straighter up and down trajectory, though they can also drift quite a bit on a parachute. Amateur rockets are typically limited to about 10 kilometers altitude, although a few world record setters have gone to suborbital type flights of more than 100 kilometers. Drones are generally limited to about 5 to 6 kilometers because of the line of sight required for remote control. This is also their benefit in that they can be brought back to their point of origin. The amount of material that LADCAP samples is dependent upon the time in which the vacuum pump operates. Balloons provide the longest sampling time with flights typically over several hours. Rockets, on the other hand, usually have the shortest flight times, at best only a few minutes. And then drones are in between. Drone flights are limited usually by their battery time, and as such, about 20 to 30 minutes. The cost to use each lift vehicle varies quite a bit, even within each vehicle type. For a balloon sat, the initial cost is going to be around $500 for the GPS and telemetry electronics necessary to track the balloon at the end of its flight. Each launch also costs an additional $500 for the balloon itself and the helium necessary to fill it. High-power rockets start at about $100 for the most basic models. A launch system is also required. This will be another $200 to $500. And then each launch requires about $30 or more depending upon the engine size required for the altitude desired. Rocket engines can easily exceed $200 for the most high-powered types. Drones have the highest initial cost. High-end consumer drones can easily exceed $1,500. However, the cost to operate them is essentially free, because the battery recharge is a few cents at most. Each of these then has their advantages and disadvantages. For the rest of this talk, I'm going to focus on the use of mid and high power rocketry. For the initial flight tests of the LADCAP, I will be using a LOC Precision Hi-Tech model rocket. This is a mid to high level model rocket capable of using mid-level F and G engines that don't require any special permits or license, all the way up to high power level 2 J engines. Between these two, we have a flight envelope of between about 180 meters and a little over 2 kilometers. The Hi-Tech is a commercially available kit that includes a payload bay capable of fitting LADCAP. Since it has already been flight tested numerous times, this provides a safety feature that we don't have to worry about incorporating into the designs. Later models and later testing will include more customized rockets fitted directly to LADCAP. This diagram shows the relatively simple yet robust nature of the Hi-Tech rocket. At the right, at the aft end of the rocket, is the J570 composite motor. This is the largest motor that this rocket can handle and will provide flights of up to about 2 kilometers. Ahead of that is a nylon parachute that returns the rocket safely to Earth over a period of about 5 minutes. At the forward end is the payload bay that contains the LADCAP device. This shows summary data of 2 simulated flights of the Hi-Tech rocket with the LADCAP payload. In the first flight, it uses an F-42 engine for a minimum altitude test flight. This is the smallest engine that can be used with this rocket and have a safe flight and recovery. It's only used for testing purposes since the sampling time is less than half a minute. The other summary is for the maximal J570 engine that provides a flight over 2 kilometers and a sampling time of almost 5 minutes. This is the largest engine that this particular rocket can use. Flights requiring longer sampling times would require a different rocket with larger engines. Thank you for your attention. While I can't answer questions directly, I would happily answer them by email. For those who are interested, animated flight simulations created with RockSim 10 follow this part of the presentation. Thanks again for your attention.